So hopefully the exam went well for you guys. Did it go well? Yeah, okay, good. Huh? Okay, but anyway, near the end of class, I'll ask you, let's say around 9:40, 45, log into the Blackboard Collaborate Ultra. So I'm gonna conduct a poll again, see whether you wanna continue the teaching model we have been doing for the, before first exam, or you wanna switch to the more classic way. Just, you don't have to, you're not required to watch the video. I will not upload the video, obviously, if it's the classic way, or we're gonna continue. But basically, I'd let you make a choice. Okay? But I will only take whoever the vote on the Flexible Collaborator Ultra. Otherwise, the counting hand takes time, right? It's faster read from there. Yeah.
I have a question about the next exam. I saw the syllabus that it's on the 11th, but is it pushed back because this exam is pushed back?
No, I will not push back. Because if the things will be completed, then we have an exam. Yeah, that's the thing. Basically, the reason I push back is because of the have to, let's say, considering I want you guys to have a thorough understanding, especially for spectroscopy part. So I kind of go a bit slower than originally expected. So that's why I did push back. But if the chapter will be done, then for exam will be, you will have the exam as scheduled. If okay. Anyway, so we were talking about this reduction of carbonyls and the hydrogenation of carbonyls. They work in the same way as the hydrogenation of alkenes, which we learn organic one. So I will not spend a lot of effort there. If you think you need refreshing that part of knowledge, go check the organic one, lecture slides, textbooks, those things. Okay, but the new type of way to reduce carbonyl group is metal hydride. So there are two kind of metal hydride. One is a sodium boron hydride. The other one is lithium aluminum hydride. And these two reducing agent can be viewed as basically, the combination of the spectator ions, sodium cation for sodium, the sodium boron hydride, and the lithium cation for the lithium aluminum hydride. So the combination of spectator ions and the real anionic active nucleophile. Okay, so in case sodium boron hydride is BH4 minus, in case lithium aluminum hydride is AlH4 minus. So those two anions are real, the active species will be reacting with the carbonyl. So the key reactivity, and these two guys are anions. So anions typically can serve as what kind of reagent? Anions typically serve as nucleophile. Okay, anions. Okay, and then the carbonyl carbon is highly positive polarized. So carbonyl carbon will be attack of the either sodium boron hydride, the BH4 minus or AlH4 minus, and the both reagents react in a similar way. Basically, if sodium boron hydride, you would give a hydride to the the carbonyl carbon, and the hydride add to carbonyl carbon. That's addition step. Okay? That's usually the rate limiting step. Then this guy can take a proton from the solvent or the reagent adding second step. Now the major difference between these two guys is that AlH4 minus is substantially more nucleophilic because the Al is a less electronegative element. So it has a better ability. So makes this guy, because these two ions both consist of hydrogen and the group 3 elements, has a single negative charge. So the more electronegative the group 3 element, the central atom is, the entire thing will be less nucleophilic because of the, this element going to be better with the whole negative charge towards itself. Okay, but because alumina is less electronegative, so this guy is more nucleophilic than this one. Okay, that's the difference. Okay, so in terms of the the reactivity difference, the lithium alumina hydride can reduce all form of carbonyl groups. All form of carbonyl groups. So the kind of carbonyl group we see here is basically there's a two let's say in this chapter we can only see two types of carbonyl groups. One kind of carbonyl groups is the called ketone or aldehyde. That means A, B is equal either hydrogen or hydrocarbon groups. Okay, this is called ketone or aldehyde. So if one of A or B, at least one of them is a hydrogen, we call it aldehyde. At least one of them is a hydrogen, we call aldehyde. So this one is an aldehyde, and this one is aldehyde. Okay, but if both sides are hydrocarbon, let's say this one is ketone. So this is the ketone. These are ketone and aldehydes. So the ketones and aldehydes can be reduced by any reducing reagent you have learned in this chapter. Hydrogen will reduce the ketone aldehyde carbonyl, and the lithium alumina hydride will be able to reduce ketone aldehyde, and sodium boron hydride also can reduce. Okay, so all those things can be reduced by all ketones aldehydes can be reduced by either hydrogen catalytic hydrogenation or metal hydride reducing agent. And the difference is reaction conditions. Okay, so if sodium boron hydride, okay, because it's less nucleophilic, so you actually can use in water or alcohol. This can be used as a solvent. So sodium boron hydride will not react with water or alcohol unless, in a normal way, means as long as you don't put sodium boron hydride in water, alcohol for, let's say, days, okay? You put like a couple of hours, they are fine, okay? So basically the reactivity of sodium boron hydride, the nucleophilicity is not high enough, so you can take a proton away from water or alcohol, okay? So that actually gives you some convenience. You can actually mix sodium boron hydride with aldehyde. Okay, let's say this one, you can mix sodium boron hydride and the water. Okay, so this can give you the reduce the aldehyde into alcohol. So why you need a solvent? Because of if you look at mechanistically, just sodium boron hydride. If just sodium boron hydride, this is negative charged, okay? You will donate a hydride to the carbonyl group, and that usually considered rate limiting step. And then you will still, this guy is anion. You will still need a proton from somewhere. where you can get that proton? The proton is from water, okay? So if I color code it, let me color code it, okay? So the water, let's say make it green. So the sodium boron hydride, let's make it blue. So the so I want to be very clear, you know, the which hydrogen come from what source, okay? So if you're doing this, okay, then the hydrogen on the carbonyl carbon come from the hydride reducing agent. Yes? Basically the hydride means this pair of electrons will be donated to the carbonyl carbon, forming a bond here. Then then this is addition reaction. Then double bond, the pi bonds open, become lone pair. So it becomes this. This break, so become BH3. See, this BH bond breaks. So they become this BH3, okay? And then then in the next step, you know the water. You will get the product, okay? And obviously, you know this is gonna become hydroxide ion. And in reality, hydroxide ion will combine with BH3, but that we don't need to worry, okay? So that is the reaction. So the key feature is when you know when the carbonyl is reduced by sodium metal hydride, the two hydrogens although overall we add two hydrogens across the carbonyl group, but the two hydrogens are from different sources. So the hydrogen on carbonyl is coming from the metal hydride. Hydrogen on the O coming from the solvent, okay? Or the second step added the acid, okay? If using lithium aluminum hydride, mechanistically is the same, but lithium aluminum hydride is so reactive, so you cannot let it mix with alcohol or water, because if you do such mixing, the lithium aluminum hydride is so nucleophilic, so basic, it will take a proton from water or alcohol, deactivate the lithium aluminum hydride. So you can treat lithium aluminum hydride just like a Grignard or organolithium. So in this case, let's say, if you do the exactly same reaction, let's say we do here, okay? Then if you do the lithium aluminum hydride, okay? And in this case, you have to using THF or diethyl ether as the first step, okay? No water, okay? And the second step, you can add water as acid, okay? And but mechanistically, it's the same as the sodium boron hydride. So I will not be repeating here, but the final product is the the add hydrogen on the carbonyl carbon, and you can have a hydrogen from the carbonyl oxygen, but the hydrogen from carbonyl oxygen from the second step of water itself as acid. Okay? So that's the difference between lithium aluminum hydride and the sodium boron hydride. So obviously, if just reduce ketone aldehyde, you certainly prefer sodium boron hydride because you don't have to do two steps, just using water or alcohol as a solvent. Single step will work. Okay, so that's if you want to reduce the just ketone aldehyde, you just use obviously with the sodium boron hydride because it's less reactive and easy to store it. Okay, lithium aluminum hydride you have to seal it really well. Okay? Otherwise, after a few months, it will be deactivated. Moisture can kill it. Okay? So the sodium boron hydride is a solvent of choice, reagent of choice if you just want to reduce aldehyde or ketone, because sodium boron hydride is reactive enough to reduce carbonyl aldehyde or ketone carbonyl, but is not reactive enough, so you can use water and alcohol as a solvent. Okay. So last example about sodium boron hydride is, let's say if you have this ketone, and if using say sodium boron hydride and using say methanol as a solvent. Okay, so in this case, and I hope you can see that the carbon skeleton no change, and the carbonyl carbon will receive a hydrogen from sodium boron hydride. Okay, and then the carbonyl oxygen will receive hydrogen, the acidic hydrogen from methanol. So which acidic hydrogen is acidic? This one is acidic. So you will get this one as a product. Okay. And very similar reaction if we have this guy. Okay. If we have sodium boron hydride, but it's deuterated. Okay. And then you have CH3OH. Okay. In this case, you will see the D will be added to the carbonyl carbon. Okay. And the H will be added to the carbonyl oxygen. Okay. And so what is if reducing ketoaldehyde, certainly we will prefer sodium boron hydride, but what's the point of lithium aluminum hydride? So lithium aluminum hydride, okay, is particularly useful to reducing some carbonyls that cannot be reduced by sodium boron hydride or catalytic hydrogenation. So like what kind of carbonyl cannot? This carbonyl cannot be reduced by sodium boron hydride or catalytic hydrogenation. So the question is, I want you understand now why this carbonyl, okay, is more difficult to reduce than the right side carbonyl. Why? Okay. So the key reason is if you look at this carbonyl, okay, you have lone pair bearing oxygen atom bound to that carbonyl. So as we know, at least when using a metal hydride as reducing agent, the metal hydride, okay, as I showed here, metal hydride serve as a nucleophile, attack carbonyl carbon. So the reactivity of carbonyl depends on its electrophilicity, right? The reactive carbonyl depends on the electrophilicity of carbonyl carbon, means how much positive charge you have on the carbonyl carbon. Okay, so when you have a carboxylic acid, you have this, the oxygen lone pair. You will be able to write this resonance form. So in this resonance form, the oxygen lone pair is donated into the carbonyl group. So that makes the carbonyl group, if you look at this resonance form, now the positive charge is on what? On oxygen, right? Oxygen, yeah, it could be nucleophilic attack, but such attack will not be productive, will not give you a stable product. Okay, so the involvement of this resonance form makes the carbonyl carbon substantially less electrophilic compared to this, because the lone pair, oxygen lone pair, is donated to the carbonyl carbon, makes it less electrophilic. Okay, so that's why carboxylic acids, okay, they are less electrophilic than ketone or aldehyde, and carboxylic acid cannot react with sodium boron hydride, cannot react with catalytic hydrogenation. So only thing can reduce carboxylic acid is lithium aluminum hydride. That's only thing. Lithium aluminum hydride. Okay. So if you want to reduce carboxylic acid, you just have to using lithium aluminum hydride. Okay. So if you want to reduce this, okay, typically you want to use 1 lithium aluminum hydride. Then in the second step, you add some water to to work up, and then what you get is you will get you will get the 2 hydrogen, okay, on the carbonyl carbon, okay, and then the O remains the same, and that this hydrogen is from the the water. Okay, so that is the difference between lithium aluminum hydride and the sodium boron hydride. Lithium aluminum hydride is you can consider is the sodium boron hydride received a power up. Okay, more powerful version of sodium boron hydride. Mechanistically, they react exactly the same. Just lithium aluminum hydride is a more powerful, nucleophile, more powerful reducing agent. Okay. Now what's the biggest difference between metal hydride and the catalytic hydrogenation is that catalytic hydrogenation does not have too much selectivity between CO double bond and the CC double bond. So if you want, if you do catalytic hydrogenation here, then likely both will be reduced. Okay, both CC and the CO double bond will be reduced because we already learned in chapter what? Inorganic 1. I forgot which chapter. CC double bond can be reduced by catalytic hydrogenation. Now we learn the CO double bond also can be reduced. So it's hard to selectively reduce one of the double bonds, one of 2 double bonds using catalytic hydrogenation. It's hard. I'm not saying impossible. Okay, there's a subtle reactivity difference, but really hard. Okay, to selectively reduce one of them. Okay? But if you use sodium boron hydride or lithium aluminum hydride to reduce this guy, you guess which one will be reduced? Let's say if you use sodium boron hydride, which one will be reduced if you guess? Which one? That's carbonyl carbon. Thank you. That's why carbonyl carbon? Because the nucleophile is ionic. PH4 ionic will attack a polar functional group, and the CC double bond is either considered completely nonpolar or very very weakly polar. So you will not be able to attract the nucleophile attack that well. Okay. On the other hand, carbonyl group is highly polar. A carbonyl group is the carbonyl carbon has a large positive partial charge. So the carbonyl carbon will readily attack of nucleophile. So this you can actually using excess amount of sodium boron hydride. Only the carbonyl group will be reduced, and the CC double bond will not be reduced at all. So that this case, this is especially useful to selectively reduce the CO double bond in the presence of CC double bond. So that's the special feature of the the metal hydride reducing agent. So any questions so far? Yes.
The structure, yeah, the one that's reacting with the lithium and hydride.
Yeah.
Why is it 2 inches in the bottom?
Well,
Why is it 2 inches?
because you look at here, this this O actually one of the O's will be gone. Okay. So this mechanism is actually more complicated than just ketone aldehyde. Okay. So if you really want to look at it, okay, basically, well, this is a good point. You catch that. It's not something mistake, but just if you really want to know, it's basically this is the first step. Okay, you're gonna have the hydrogen on here. OH, okay, and then the other one will become alumina. And this is a good Lewis acid. So this one actually can combine with this. Okay, so just due to the limit of time, so I didn't want to go through the entire process. But anyway, so what you'll be seeing is you're gonna form this complex. And then this this because alumina actually is element has a very strong oxyphilicity, so this bond can actually break. Okay, so this whole thing can actually leave. So you can consider eventually this all the hydrogen can be all the hydride can be given so that this this H could become connect to the other alkoxide. OH, OH. Then once all these the hydride is donated, then the O can actually this bond can actually break, and then after it breaks, this thing can come in. Okay, then it form at one point become aldehyde. Then can receive the attack of aluminum hydride again. Okay, so this proton, okay, can be taken away by the when this this one breaks, you can consider the easiest way you can say this proton can be transferred to this oxygen, so it become HO alumina. So then once you have aldehyde, then you can further attacked by aluminum hydride. Okay, but because it's the kind of mechanism we were not really seeing, the in future. That's why I didn't want to spend much time on it. But the thing, just the key part is alumina is actually a very powerful Lewis acid, so you can capture the oxygen, then take the oxygen away. Okay. So any other questions on this? Okay. So then that's the metal hydride reducing agent. Okay, it's pretty much the same for the boron stuff. Okay. So if you have a carboxylic acid, then you only thing can reduce it is using the lithium aluminum hydride, nothing else. Okay. Now besides reduction of carbonyl groups, the can prepare alcohol. Alcohol can also be prepared by reacting, another nucleophile with another electrophile. So the nucleophile is something we learned in chapter 15, is either organolithium or Grignard reagent. So the organolithium or Grignard reagent, I hope you guys recall what I told you. So the organolithium MgX we consider is equivalent to this one. The magnesium or halide, whatever, it's just considered spectator ion. Similarly, organolithium, for the first principle approximation, we also consider its supply of carbon anion. So this kind of carbon anion, if you let them mix with a kind of compound we have learned in chapter what? I think it's chapter 8, organic 1. You have the 3-membered ring with oxygen called epoxide. So the epoxide is the only type of ether that is highly reactive. So you probably can guess why epoxide is highly reactive. What feature makes epoxide highly reactive? Huh? Strong base? No, it's not.
It's the site.
So see, look at it. The THF is a very stable solvent. Okay, pretty stable solvent. Okay, but the epoxide is a highly reactive compound. So both of them are the same class of compound. Both of them are ethers. You will learn more in chapter 17, I believe. Ethers. Okay, both of them are cycloethers. So what's the difference between these? What's the biggest difference between these two guys? The right side one is unreactive, but the left side is very reactive. Yeah. Yes, bonding angles. Okay, because of the epoxide has a bonding angle approximately 60 degrees, and they want what kind of bonding angle they prefer. Yeah. Yeah, very good. 10, 110, let's say, easy 110. So it's very large angle strength. So that makes this kind of guy very reactive. Okay, and then make it very reactive means they want to release, because the reactivity comes from the angle strength. So in the reaction, the molecule would like to open the ring, then the angle strength will be relieved. Okay, that is just the thermodynamics. Okay, because of the angle stress, you want to relieve the angle strength, but kinetically, how do we open the ring? Then will depend on whether your reagent is highly nucleophilic or highly electrophilic. Okay. So because of this ring is a polar compound, you have a high negative charge here, right, and a high partial positive charge here. So if you have a electrophile, they will react with oxygen. If you have a nucleophile, you will react with what? Carbon, ring carbons. Okay. So now the thing is, I want you to think with me, okay? So if you have, say, methyl lithium, so methyl lithium we can consider is just supply of methyl anion, is one of the most powerful nucleophile you can find, okay? So then you will attack, okay? No question, attack one of the ring carbons, right? Because of those two ring carbons, they are positive polarized, they are electrophilic. Now the question is, now if this methyl anion attacks one of the ring carbons, I have to break the bond. Which bond I should break? Say the hydrogen, they have two hydrogen there, okay? To maintain the 4 bonds, if the methyl carbon bound to the ring carbon, so the existing 4 bonds will break, right? One of existing 4 bonds will break, but which bond will break? So the key part I want you to think with me, okay? First question, which bond will break? Okay, so why break that bond, not the other bond? So to answer the question, you need to look at by breaking a bond, okay, one of the 4 bonds, what kind of chemical species you will be getting. So what kind of group will be leaving the molecule? So basically, you need to look at the leaving group quality. So the first, obviously, we were not breaking any of those green CH bonds, okay? Because if you break the green CH bonds, you will not relieve the ring strand, angle strand, right? Because if breaking the CH bonds, the 3-member ring is still there, okay? You need the thermodynamic driving forces, you need to break the 3-member ring, give you the angle strand, okay? So to break the 3-member ring, you must break the carbon-carbon bond or carbon-oxygen bond, okay? You're not going to break the CH bond. Is that clear? Not break the CH bond, okay? But now if you look at it, if you just narrow down 2 choices. If you break the carbon-carbon bond, what kind of chemical species you are getting, okay? If you break the carbon-carbon bond, let's make it red, okay? If you break the carbon-carbon bond, okay, what kind of species you are getting? You are getting the CH3, okay, bonded to that ring carbon with 2 green hydrogens, okay, bound to it, okay, then bound to the O, bound to the C, H2, because this one breaks, okay, give you this one, okay. So this is the product, positive product 1, okay. Then you look at positive, this is only one pathway. The second pathway, if we break here, okay. I'm just using the CH3 connect to the carbon with 2 green CHs, okay? Then you will connect to CH2, connect to this. So which leaving group is better? Yes? The oxygen one, because of the, very good, the oxygen one basically has it's a normal strong base, not some exceeding one, okay? It's ordinary strong base. And the top one is a super base, just like a green area, a super base. So as far as leaving group quality is concerned, the bottom one is orders of magnitude better than the top one. That's why we break the CO bond. We don't break the carbon-carbon bond. I want to think with me. Don't just memorize it, okay? It's judged by leaving group quality. So I guess we can just maybe pause at this point, okay? Then please logging to the Collaborate Ultra, so I can give you guys the poll, see whether you want to continue with the current instruction mode. Basically, have watched I'll post the video first. You're gonna be watching it, okay? or just go back to the more traditional one. So,
If we do the traditional, we would have to come in 10 minutes early. If we do the traditional version, we would have to come in.
yes, you have to come to 7:50 to take that, the 10 minutes quiz.
We do the oral one.
Well, let's say, the multiple choice, okay? So first answer is upload a video you watch before class. Quiz starts at 8, okay? Second one, no video watching before class. Quiz starts at 7:50. Maybe a third choice?
Third choice?
Third choice, no video watching. Quiz starts at 8. 6 minutes. Okay, your choice. Okay.
I don't know. I like the.
We do the oral one. And the oral one is that.
That's the right answer. That's the highest truth.
You vote. I'll take one up.
Can I just raise my hand and
No, I just look at this. I don't count hands. Okay. Just do it here. Do it here.
Yo, who's the
Wait.
Three, bro.
Come on.
Ricky, what's the right answer? I don't know. I'll go to one the right answer.
Huh?
We do like a handful.
Really?
We do like a handful.
Handball is difficult to count. It's a lot of Okay, handball. Everyone, okay.
They keep flipping from like.
Oh, okay.
Yo, bro, someone pick me.
Okay, so choice 1. Okay, choice 1. If you agree, raise your hand.
What,
Choice 1, first one. You watch before class. Quiz start at 8. Okay, please hold your hand to the top. 1, 2, 3, 4, 5, 6.
Wait, you sure?
11, 12, 13, 14, 17, 18. Okay, you already more than half. So
Okay,
no,
we win.
Okay. No further voting. Can you do it? More than half already. Okay, so continue. We will continue the current instruction mode. No, not much revolt. So that we know, and you count more than half already, so that forget about it.
Who voted 3, bro?